Imagine a world in which humans have mastered reliable, fine-grained control over local weather, able to summon rain over a drought-stricken valley, dissipate a thunderstorm above a festival, or create a mild, clear microclimate over a coral restoration site. This is not mere meteorological tinkering, it is a civilizational inflection point. The capacity to reshape mesoscale atmospheric processes on demand would ripple through economies, politics, ecology, ethics, and culture. Below I explore the scientific plausibility, immediate uses, systemic consequences, potential conflicts, and the philosophical questions such power would raise. 1. The technological premise. From geoengineering to mesoscale mastery, today's weather modification techniques, cloud seeding, aerosols, marine cloud brightening, operate with limited predictability and scale. A hypothetical leap to robust local control would combine several advances: high-resolution atmospheric sensing and modeling, targeted actuation ionization arrays, airborne condensate generators, micro-drone swarm seeding and mixing air masses, real-time data assimilation, and autonomous control systems guided by eye. Crucially, control must be both spatially precise, hundreds of meters to tens of kilometers, and temporally responsive, minutes to hours, with validated safety margins to avoid cascading unintended effects. From a physical standpoint, mesoscale atmospheric dynamics are chaotic but not unconstrained. Small perturbations can be amplified under particular boundary conditions. Mastery implies we can predict and steer those amplifications rather than merely nudge them. That requires reducing epistemic uncertainty in initial conditions and having a suite of actuators capable of changing energy, moisture, or aerosol distributions at the relevant scales. 2. Near-term applications and benefits. Agricultural resilience. Farmers could schedule irrigation rainfall during critical crop stages, reducing yield variability and the need for energy-intensive irrigation. Crop insurance losses from drought and frost would shrink. Disaster mitigation. Preemptive dissipation of convective storms over cities, targeted fog clearing for airports, or induced precipitation to reduce wildfire fuel loads could save lives and infrastructure. Urban climate management. Cities could cool heat islands during extreme heat waves, reducing mortality and energy demand. Microclimates could make dense urban areas more livable without massive infrastructural overhaul. Biodiversity and restoration. Localized rainfall could enable reforestation corridors in arid zones or protect delicate ecosystems during heat stress. Coral restoration might be aided by creating slightly cooler, cloudier conditions during bleaching events. New industries and tourism. Weather as a service could emerge: luxury estates or resorts guaranteeing sunshine, festivals promising perfect conditions, and sporting events guaranteed dry grounds. Tourism could spatially and temporally decouple from traditional climatic constraints. 3. Economic reconfigurations. When weather becomes a managed resource, it acquires economic value and becomes tradable. Several novel markets and institutions would arise. Weather credits and markets. Regions might sell precipitation or cloud cover rights to cities or corporations. Markets would price access to favorable microclimates, analogous to water rights or carbon credits. Insurance transformation. With lower meteorological uncertainty, some forms of insurance would shrink, others, covering technology failure or malicious interference, would expand. Agricultural realignment. Crop zones could move beyond historical climate envelopes, enabling new monocultures, but also upending rural economies reliant on climate specificity. This would benefit agribusinesses capable of paying for reliable weather while disadvantaging smallholders. Infrastructure investment. Cities and private actors might invest in local weather infrastructure as they do today in ports and airports, creating a long-term asset class, maintenance heavy, regulated, and strategically important. 4. Geopolitics and the risk of climate conflict. Control over weather is inherently strategic. Weather systems do not respect political borders. Any local intervention risks downwind consequences. Several geopolitical dynamics would follow. Weaponization and deterrence. Weather control could be repurposed for coercion, dampening rainfall over an adversary's croplands or amplifying storms to disrupt logistics. The line between humanitarian intervention, e.g., inducing rain to alleviate famine, and coercive manipulation is thin. Asymmetric leverage. Wealthy actors, states, corporations with advanced weather infrastructure could exert influence over poorer regions through economic contracts or political pressure, offering precipitation in exchange for concessions. Arms control analogs. Treaties and norms would be required to prevent hostile uses, analogous to the partial test ban and biological weapons treaties. Verification would be technically challenging. Distinguishing natural variability from deliberate intervention requires transparency in modeling and instrumentation. Transboundary externalities. International legal frameworks would need to address liability for unintended impacts, crop failures, floods, or ecosystem disruptions downwind of manipulation. Principles of transboundary harm and common but differentiated responsibilities would be tested. 5. Environmental and systemic risks. The atmospheric system is interconnected and nonlinear. Localized control reduces some risk while creating others. Cascading consequences. Removing clouds in one place might intensify storms elsewhere. Inducing rain to relieve drought could deplete moisture and change regional circulations. Ecosystem mismatches. Creating ideal agricultural microclimates may support crops that are adaptive in the short term but undermine soil health, pollinator patterns, or seasonal cues for fauna, leading to ecological drift. Dependence and fragility. Societies may become dependent on technocratic weather systems, losing resilience and traditional coping strategies. Technology outages, cyber attacks, supply chain failures, or systemic errors could precipitate rapid crises. Moral hazard. If weather can be fixed, there may be diminished incentives to mitigate greenhouse gas emissions, slowing global climate action and exacerbating long-term climate risks. 6. Ethical and social implications. Justice and equity. Who decides which places get weather control? Prioritization could reinforce existing inequalities. Urban centers and affluent regions first. Marginalized communities, often the most climate vulnerable, risk being last in line. Consent and participation. Local populations should have autonomy over interventions that affect livelihoods, yet in a world of externalized weather dependencies, genuine consent is complex. Democratic governance of atmospheric interventions will be essential. Value pluralism and cultural meaning. Weather carries cultural and spiritual meanings. Manipulating it could erode traditions, seasonal rituals, agricultural calendars, even aesthetics of landscapes. Conversely, it could enable cultural practices otherwise impossible under changing climates. Attribution and responsibility. When a weather actuator causes harm, who is responsible? The operator, the manufacturer, the programmer of the control algorithms, or the state that licensed the technology. Law and moral philosophy will need to adapt notions of foreknowledge, acceptable risk, and collective responsibility. 7. Governance, norms, and technical safeguards. Robust governance should combine technological design choices with institutional constraints. Transparency and auditing. Public registries of weather control deployments, independent verification of models and outcomes, and open-source elements of control algorithms would reduce secrecy-based misuse. Tiered access. Prioritize humanitarian, ecological, and essential public uses. Limit luxury or purely commercial manipulations unless they demonstrate no cross-boundary harm. Adaptive regulation. Rules must be able to evolve with scientific understanding, with sunset clauses and iterative review. Fail-safe design. Systems should default to safe modes under uncertainty, e.g., passive damping of interventions if predictive confidence falls below thresholds. International treaties. A framework akin to environmental commons governance, integrating scientific verification and dispute resolution, would be necessary to manage transboundary risks. 8. Cultural transformations. Aesthetics, imagination, and new rituals. Weather management would reshape human relationships to nature. The sublime unpredictability of storms and seasonal cycles has inspired art, religion, and philosophy, existential anchors that may shift under engineered skies. New aesthetics. Curated skies could become a medium for artistic expression. Light shows, timed auroras if we push ionospheric manipulation, or city-branded microclimates. Ritual and identity. Some communities may resist intervention as a defense of identity and autonomy. Others may incorporate controlled weather into celebrations and rites. Psychological effects. The perception of mastery over nature may bolster human hubris or provide comfort against existential climate anxieties. The long-term psychological consequences of living in technologically smoothed environments are uncertain. 9. Thought experiments and futures. Consider to plausible trajectories. Democratic stewardship. Weather control becomes a public utility, tightly regulated, prioritizing resilience, equity, and ecological health. International institutions mediate disputes. Technology is used primarily for disaster mitigation, agriculture support, and biodiversity protection. Market-driven capture. Private firms and wealthy states treat weather as a commodity. Microclimate enclaves proliferate, inequality deepens, and geopolitical tensions rise as downwind harms accumulate. The short-term gains are offset by fragile social-political systems and escalating transboundary conflicts. 10. Philosophical reflection. Control, humility, and responsibility at a deeper level. The possibility of local weather control forces us to confront perennial philosophical questions. What does it mean to master nature? Does increased control constitute moral progress or a heightened form of hubris? Control can be an expression of care, relieving suffering and protecting livelihoods, but it also changes the human condition. Agency shifts from acceptance and adaptation toward engineering and continuous management. With that shift comes a moral imperative: to exercise stewardship with epistemic humility, to embed justice in technological design, and to cultivate governance norms that respect ecological limits and human dignity. Conclusion: local weather control, if it becomes feasible, is a technology whose promise and peril scale together. It offers potent tools to alleviate suffering, bolster food security, and make cities more livable. Simultaneously, it threatens to concentrate power, produce new forms of ecological fragility, and prompt geopolitical competition. The critical lesson is not merely technical. It is institutional and ethical. We must build the social infrastructure, laws, norms, participatory governance, education, and international cooperation before or alongside the technology, not after. Only by marrying scientific capability with democratic stewardship and ecological wisdom can we hope to turn the cloud of possibility into a forecast that serves humanity equitably and sustainably.